So that's the basic difference, right? Blanking and piercing. That depends on which is your desired object. So once this was a blank, right? You had taken it from a strip, right? But then again, when you wanted to remove, you wanted to have some circular cutout here. So when you remove that, this is your scrap now. That is a desired part, right? So a very good example here to show clearance in sheet metal cutting. So this is very important. The distance between the punch and the die, there has to be a clearance maintained. Typical values range between 4 and 8% of the stock thickness. So it depends on the thickness of that sheet we are trying to form or cut. If it is too small, the fracture lines pass each other, causing double burnishing and larger force. Basically, clearance is the gap. Let me show you. If this is your punch and this is your die, right? And the punch is basically responsible for, the punch will move up and down, right? So, and it cuts or shears off or forms, right? Whatever it does, depending on the forming process. What we are saying is this distance, right? This gap that is there, that is called the clearance, right? In simple terms, that is your clearance. So it depends if this is a circular die and punch, you would have a circular clearance, right? If it is a prismatic shape, as in a square or a diamond kind of shape, it depends. But the gap between the punch and die is called the clearance. So if that is too small, if the clearance is too small, then the fracture lines pass each other, or in double burnishing larger part. Basically, when the punch is trying to remove the material will pass through this type. It will shear off, okay? But after shearing off, it will not come out of the die instantly. It has to travel some distance. You have to ensure that the distance traveled does not cause damage to either the punch or the die or the sheet that has just been removed. So if the clearance is too small, then you have fracture lines passing each other and therefore double burnishing. So surface finish will be affected. If it is too large, the metal is pinched between cutting edges and excessive burr results. Basically, if that is too large, you will not have proper force to shear it off. So that will be a problem with insufficient force, if you want to call. And therefore, the material is pinched between the cutting edges. Basically, you will have some improper or imperfections that it was not able to shear off properly. Excessive burr results, right? Burr is basically a irregular strap or sheet, irregular shape of the metal, or the part where you have the sheet contacting the die, right? That is the perimeter of the sheet. I hope that is clear, right? No doubts. Okay. So clearance in sheet metal cutting, what should be the recommended clearance? How much clearance should be? Not too large, not too less, right? Not too high, not too less. What to do then? The recommended clearance can be calculated by C is equals to AT. What is C? So clearance, as we know. A is the allowance and T is the stock thickness. So it's dependent on the stock thickness, you can say, right? Depends on the thickness of the part that is being either bent or formed, right, or sheared, etc. Allowance A is determined according to type of metal. So that A is basically dependent on the type of material, right? Basically metal. We are talking about metal form, right? Allowance A for 3 sheet metal groups. As you can see, for aluminum alloys of this grade 1100S and 5052S, all tempers in the sense they differ based on the tempering heat treatment. Basically, we are talking about. So depends on that heat treatment. So if the first category is 1100S and 5052S, then you have to have allowance A as this value 0.045. So it depends on all these characteristics. You have different A values, allowance values assigned to these metal groups. And then you have the punch and die sizes for blanking and punching. So for a round blank of diameter dB, right? It's a round blank that you want to cut out. So if that is dB, then the blanking punch diameter is dB minus 2c, right? Because when you're talking about round or cylindrical entities, then you have to consider two sides, as we have discussed in the last slide. There are two sides, two clearances, right? But how do you calculate it for a round object, right? Then you have to subtract two types, the clearance, because clearance is present two sides. So that subtract the diameter, subtract that clearance from the diameter, and as for a round hole of diameter dh, if dh is a hole punch diameter, then the whole die diameter should be dh plus 2c, right? Same thing. Because this is a whole round hole, you have kept some extra gap, isn't it? More than the whole punch diameter. I mean, if you're adding 2c, right? That 2c factor is basically added for the whole case of a hole, and for blank you have removed that, right? For blanking punch diameter, isn't it? Because the crunch has to be smaller and the die has to be made larger to compensate for those effects which you have discussed in the last slides. You can see here, you see dh is your punch size, and C here you can see that this is the gap, that is a clearance gap, and the die size, as you know, is from left side to right side. This from here to there you have the die size. So the die size determines blank size dB, punch size determines the hole size, C is your clearance, right? Angular clearance. So die, as you might have observed in the last slide, right? Last few slides, the die is basically having that. This was way back. So it will be having a taper, right? Basically angular clearance, if you want to call it. What is the purpose? It allows slug or blank to drop through dry, right? Isn't it? Because if that taper is not there, then you would have friction, right, all the way down when it leaves the die. So therefore, you have allowed slug or blank to drop through the die. It has some straight portion, as you can see, and then resharpening. Basically, because of the friction, the surrounding periphery of that sheet will sharpen, removing of the burrs, etc. And we have then the angular portion, the angular clearance that is there. The value between 0.25 to 1.5 is very less, not generally visible to the naked eye, right? Of the order of 1 or 2 degrees. We're not able to distinguish. If only we can measure, right, then we can say this much is the uh, angular clearance, right? Cutting forces, these are also important characteristics for determining the press size. If the force we know that, for example, this component, this material requires so and so force to either cut it, basically shearing, or to form it, right, for a given shape, let's say, then it depends. I mean, when you have those forces finalized, then using those forces, you can decide the press size, right? Because they come in tons, like 110, 210, 10, 10 also, 100 tons press also, depending on the force that it can exert. So that force will decide based on the material that you want to form, right? Based on the strength of the material. F is basically S into T into L. What is S? F is actually the force, right? Cutting force. S is your shear strength of the metal. So more is the shear strength, more force will be required, right? Obviously. T is the stock thickness, right? And L is the length of the cutting edge, which is being cut. So that is basically determining the press size. So as we know, you have the two categories, right? Bending and drawing. So we have seen some portion of it, isn't it? As for blanking and piercing, etc. But you basically have bending of it or drawing of it, right? So we can make these two categories. So it is basically forming as a reshaping of a section in a material by applying a combination of compressive and tensile stresses to induce deformation. Both compressive and tensile, not just compressive. It depends sometimes because the outer portion of the sheet may be experiencing tension because of the convex nature of the punch, right? So it's basically the reshaping of a section in a material by applying a combination of compressive and tensile stresses and basically not applying, inducing, right? To induce deformation, right? So deformation is also induced because of these stresses. And as we have discussed, two broad categories, bending and drawing. As for bending, you see, you have this straining of the sheet metal around a straight axis to take a permanent bend. So which is your bend axis? Right? I'm sorry, which is the straight axis? Straight axis is basically here. You see bend axis or straight axis is this, because this is about which this component is moving, right? It was earlier here, let's say, right? All of them were inline, completely flat. And then around this bend axis, you have bent the component. So the middle axis, right, running across the thickness, the middle axis is called the neutral axis plane, right? Where there is basically where no compression and no tension is happening. Because anywhere other than that, if you observe the outer portion of this sheet, you would observe that the outer portion has stretched, right, because of tension. And the inner portion would be subjected to compression, right? Because there is no other way to disperse the energy or the material in this particular case. So that is your bending, right? Simply stated. You'll bend around an axis, straight axis, to be honest. I mean, to be clear, right? So I think we can continue in the next class. If there are any doubts, you can ask. Otherwise, we can. Okay.